what we're going to do is we're going to show that continued fractions actually, if we're within 1 over r squared, the continued fractions will actually find the right fraction. So how do we do this? Let's consider continued fraction expansions of x. So here is x. If x equals what? Let's see. Yeah. If x equals d over r, well, we get the right answer because one of the convergents of any rational number in the continued fraction is the rational number itself. Get right answer. So here is d over r. For some interval around d over r, also get the right answer. Well, I mean, that's actually pretty easy to prove because, it's obvious the continued fractions are continuous process. So if you alter x by a small enough amount, then d over r will be one of the convergents. So let's do this for let's do this for 13/15. So what was it? 13/15 was equal to 1 over 1 plus 1 over 6 plus 1 over 2. 1 over 1 plus 1 over 6 plus 1 over 2. So let's look at 1 over 1 plus 1 over 6 plus 1 over 2 plus epsilon. If epsilon is bigger than 1, if epsilon, I want to say if epsilon is less than 1, still get 13/15 as a convergent. Why is that? Well, if epsilon is less than 1, then, you do this, then plus 1 over whatever, plus 1 over whatever, etc. So if epsilon is less than 1, the continued fraction starts out like this and then keeps on going. And if epsilon is bigger than minus a half, you still get 13/15. Why is that? Well, if epsilon is bigger than minus a half, you get 1 over 1 over 6 plus 1 over 2 over 1 plus 1 over, 1 plus ... And 1 plus 1 over 1 is just equal to 1 over 2. So if you cut it off here, it's still 13/15. Is that clear? And why bigger than minus a half? Well, if what you had was 1 over 3 halves, it would be 1 over 1 plus 1 half. Plus more terms, but we can ignore them because this is 13/15. Okay. So what is 1 over 1 plus 1 over 6 plus 1 over 2 plus epsilon? Well, this is clearly a fraction with epsilon in it, and it has to be of the form, well, I'll tell you what it is first, and then I'll tell you why it has to be of this form. It's 13 plus 6 epsilon over 15 plus 7 epsilon. And so it has to be of the form A plus B epsilon over C plus D epsilon, because if you stick that in there and then keep on doing these operations, this, 1 over 1 plus G preserves something of that form. So it has to look like this. I mean, it has to be A plus B epsilon over C plus D epsilon. Now, when epsilon equals 0, we know it's 13/15. And did anybody notice that this was 6/7? So 6/7 is the convergent before that. And if you plug in epsilon equals infinity, well, what does that do? It gets rid of this last term. So you get the convergent before that. So you get 6/7. So this is 13 plus 6 epsilon over 15 plus 7 epsilon. And when we go back here and we have 13/15, the number ahead of that is 20 over 23. Number behind that is 19 over 22. And you can see the difference between these is 1 over 15 times 22. And the difference between these is 1 over 15 times 23. And, well, these, this is R. This is actually less than 2R because it was 15 plus 7 times 1. And when you substitute in epsilon equals minus a half, then this has to be less than 3R. So this number is less than 2R squared, and this is less than 3R squared. So as long as you're within 1 over 3R squared of D over R, one of your convergents will be the right answer. And actually that's, I think the textbook has a proof of 1 over 2R squared. But this is good enough. So that tells you that you choose L to have twice as many bits, or rather 2L, your first register that you're using for the Fourier transform has to have this, has to have twice the number of bits as the number you're trying to factor, and you're guaranteed to get D over R as one of the convergents.